In this video, we're going to discuss assignment of probabilities. This is the first video where we'll start to calculate probabilities. So first, let's define probability, and we'll say probability is the measure of likelihood. So if the probability of an event is 0, that means the event cannot happen. And at the other end of the spectrum, if the probability of an event is 1, that means an event is guaranteed to happen. So notice the notation that we're using here. We're writing PR for probability, and then inside the brackets, we write whatever event we're talking about. So we read this as probability of the event. Let's also define a probability distribution. So it's a table that lists some various outcomes. So you can imagine having various outcomes described here, and then beside that, probabilities for each of those different outcomes. So that's a probability distribution. Two important properties of a probability distribution. First of all, each probability is between 0 and 1, and the sum of the probabilities, the sum of all the probabilities in a probability distribution is 1. Now, if you phrase these numbers in terms of percentages, instead of saying 0, you could say 0%. Instead of saying 1, you could say 100%. And so our probabilities range between 0% and 100% inclusive, meaning you can have a probability of 0%, you can have a probability of 100%. And if you sum up all your probabilities in your probability distribution, they will add up to 100%. So that's just a rephrasing of those two properties. So let's look at a quick example. Let's say our experiment is just rolling a die, and we're paying attention to the number that comes up on the die. So let's write out our different outcomes. What could happen? Well, we could see any number 1 through 6. So those are our different outcomes. And assuming that this die is fair, then each of the outcomes has equal probability. So the probability should be 1 out of 6 to roll a 1, 1 out of 6 to roll a 2, etc., 1 out of 6 to roll a 6. So there's our probability distribution for rolling the die, listing our different outcomes and the probabilities that are associated with them. Now let's say some students are polled on their program. The question is to determine the probability distribution. So we're just going to write PD for short for probability distribution. And what we have is some data in front of us. So imagine we walked down the hallway, took a random sample of students. So the number of students who said business was 13, number of students who said technology was 18, and number of students who said nursing was 9. So out of this, we somehow want to form a probability distribution. Well, we've already got the outcomes, because the outcomes are just the different responses in terms of what program they're in. So we know the outcomes are going to be business, or technology, or nursing. But what we need to do is calculate some probabilities, specifically the probability of a student giving a particular response. So what we're going to need here is the total number of students. So we're going to look back at our data, 13, 18, 9. Let's add those up to get a total. So the total number of responses that we had was 40. So the way we're going to get probabilities here is we're going to take each number, like 13, and divide it by the total. So let's just turn this into a decimal. So that's going to be 0.325. So you could say the probability that a student is in business is 0.325. Often we'll give our probabilities just in decimal form like this. But if you want to turn that back to a percentage, just multiply by 100. So that's the same thing as saying 32.5%. So in everyday life, we tend to talk about percentages like this. Whereas in math, it tends to be a little bit faster just to give the decimal form. Okay, let's find the probability of one of these students being in technology. We would take our 18 technology students, still just dividing by the total. So that gives us 0.45, or you could call that 45%. And then finally, take your nursing, number of students, 9 divided by 40, gives us 0.225. For me, saying 0.45 or 45% is a little bit more intuitive than saying 18 out of 40. But it's a personal choice whether you want to go the fraction route or the decimal route. So the total of all your probabilities should always be 1, and each probability should be somewhere between 0 and 1. So now we're going to toss a coin 3 times, and we're going to record the number of heads. Let's determine the probability distribution. So what we're ultimately trying to find is a list of different outcomes and the probabilities that go with those outcomes. So let's think about the outcomes first. So you toss a coin 3 times and think about how many heads you could get. Well, you could have 0 heads. If you end up getting tails, 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 you would have 0 heads. You could have 1 head in the 3 coin tosses, you could have 2 heads, or you could have 3 heads. So those are the different outcomes. And now we want to work towards figuring out the probability of those different outcomes. Now, this problem is a bit more complex than our previous one. And so sometimes you need to do a little bit of intermediate work to actually get to your probability. What we can do here is just write out a description of what it means to have a certain outcome. And then we can count the number of ways to get that outcome. And once we have this number of ways, then we'll be able to move into probabilities from there. So let's try the first row. So if our outcome is 0, that means we've got 0 heads. And let's write a description of what our coin toss would look like then. We must have had tails, tails, tails. And how many ways are there for that to happen? Well, just 1 way. So that's different than having an outcome of 1. So if our outcome is 1, that means we've got 1 head in the 3 coin tosses. And that can actually happen a few different ways. You could have heads, tails, 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 heads, tails, or tails, tails, heads. So we've got some possibilities here on which toss that head comes up on. So the number of ways is actually 3. And similarly, if you have 2 heads, you're going to have 3 different ways for that to happen. So let's think about what the description would be. You could have heads, heads, tails, heads, tails, heads, or tails, heads, heads. So again, 3 ways for that to happen. And then by the time we get to this outcome here, remember 3 is representing the number of heads, we're back down to just a description that contains only 1 different possibility. It would have to be heads, 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 only 1 way for that to happen. And now we're going to do a similar kind of thing to when we were looking at which program students were in. We would just add up the total. So total number of ways or total number of outcomes is 8. And we're going to get our probabilities just by doing things like 1 over 8, 3 over 8, 3 over 8, 1 over 8. So fine to leave your answer like that if you want to give your probabilities in fraction form, or alternatively, you can switch everything over to decimal. So I think I will do the decimal version. So 1 out of 8, 0.125, 3 out of 8, 0.375, and that way we can fill in all our probabilities. So I would say this table is just a little bit cluttered, and that's because we had to do a bit of intermediate work here to find our probabilities. So strictly speaking, when you're asked for a probability distribution, really what you're looking for is just a concise table of listing out your different outcomes and the probabilities that go with them. So our different outcomes for number of heads are 0, 1, 2, 3, and our probabilities 0.125, 0.375, 0.375, 0.125. So there's our final answer for our probability distribution. So our next experiment is we're going to roll a red die and a blue die. And first thing we're going to do is describe the probability distribution. All right, so probability distribution is a table listing our different outcomes and the probabilities of each of those outcomes. So let's start to think the different things that could happen. What it might help to do here is to just recall one of the previous problems that we did where we were rolling a red die and a blue die, and we said it might be helpful just to think of a table of the different outcomes where you maybe have your red die in the rows here and your blue die in the columns. So you can visualize that there would be 6 times 6 different possibilities for what could happen on this die, 36 outcomes in total, because essentially each little square in this table is representing an outcome. Then the other thing to point out is that rolling a 1 on red and 2 on blue is different than doing this the other way around. So when we write out our outcomes, we should really use ordered pairs, and we should say things like 1, 1, 1, 2, etc. And we should just be clear here what the first and second number represents. So I'm just going to do this as red and then blue. You could do it the other way around, but it is important to label it so that we understand that the ordered pair 1, 2 is different than the ordered pair 2, 1, and that may matter later on in the question. Okay, so I don't really feel like writing out 36 possibilities, so we can just go ... and then if you're doing this in numerical order, your last outcome would be 6, 6. So notice that it says describe the probability distribution. That means just give a sense of what it looks like. You don't have to write out all the details. And then let's figure out what our probabilities would be. So we've said over here that there are 36 different outcomes that can happen. Each of those outcomes is equally likely, so each probability is just going to be 1 out of 36. 1 out of 36, and you can just go ... last probability, 1 out of 36. So now let's use our probability distribution to actually do a calculation. We want to find the probability of a certain event. So here's our event. We want the roll on red to be even, and we want the blue roll to be greater than the red roll. So let's give this event a name. Often when we're talking about events, we'll call it capital E or capital F or something like that. So let's call this one capital E, and we'll start by just writing out the outcomes in E. So what do we want? We want the roll on the red to be even. Okay, and we've said that when we're writing out these ordered pairs, we're going to follow the convention of writing the red roll first. So the roll on red, for example, could be 2. And the blue roll to be strictly bigger than the red roll. So if the roll on red is 2, the roll on blue could be 3, 4, 5, or 6. So there we've captured all the possibilities where the roll on red is 2. Roll on red has to be even. So there would be a few more possibilities where the roll on red is 4. Remember, blue roll has to be strictly bigger than the red roll. So we could have 4, 5, 4, 6. And then let's think about what would happen if the roll on red is 6. That's another even number. Well, that's not going to work because this number here needs to be bigger than the first number. The roll on blue needs to be strictly bigger than the roll on red. So there's actually no possibilities that include the red roll being 6. So therefore, that is our complete list of outcomes. We've made sure that the first number, which is the roll on red, is even. So if you look all the way across here, yep, we've only captured even numbers on red. And we've made sure that on the blue roll, which we're writing second, that the blue roll is bigger than the red number. So we made sure that's true all the way across. Okay, so that's a complete description of our event E. And what we're trying to get at is the probability of this event E. So let's look back at our probability distribution. We said, well, each of our outcomes, no matter what they are going to have probability 1 out of 36. So to get our probability of E, what we're going to do is just add up the probabilities of each of the individual outcomes that are in E. Probability of 2, 3, 1 out of 36. We're going to add that to probability of this outcome, which is 1 out of 36. Add it to the probability of this outcome, 1 out of 36. And you probably get the idea. So we're just adding up 1 out of 36 for each of these different outcomes. So since there were 6 different outcomes in the event E, we've just added up 1 out of 36 6 times. So if you want to turn that into a fraction, that would be 6 out of 36, or you could reduce that and make that 1 out of 6 if you wanted. Or if you prefer, you could put that into decimal form, and that would look like 0.17 approximately. So about 17% probability of getting a roll on red that's even and having the blue roll being greater than the red roll. Now we're looking at an unfair 4-sided die, and our die has the following probability distribution. So we're told the different outcomes. Okay, we can see numbers 1 through 4 coming up on this die, and we're also told the probabilities of these different outcomes. Remember, the whole point of this problem is that our die is unfair. So it somehow got a weight in it so that it's most likely to roll a 2 and least likely to roll a 1. So based on this probability distribution, let's find a few different things. First thing we want to find is the probability that the roll is less than 3. So what we're going to do is break this up into cases. If the roll is less than 3, then the possibilities are that the roll is 1 or the roll is 2. And what we're going to do is just add up the probabilities of each of these events. So we're going to take the probability that the roll is 1 and add it to the probability that the roll is 2. The word or really represents plus when we translate that into a calculation. Okay, and then we can just pull the information out of the table. So the probability that the roll is 1 is 0.1, plus the probability that the roll is 2, well, that's 0.35. So if we add those together, we get 0.45, or in other words, 45% probability that the roll is less than 3. Part B, let's find the probability that the roll is odd. So again, we'll break this into cases. We'll say, take the probability that the roll is 1. So adding on the probability that the roll is 3. So there we've covered the two cases where the roll is odd. The roll can either be 1 or it can be 3. And then again, it's just a matter of pulling the data out of the question. So probability that the roll is 1, 0.1, and probability that the roll is 3, 0.3. So we'll just add those together. 0.1 plus 0.3 gives us 0.4, or in other words, 40% probability that the roll will be odd. So now let's find the probability that the roll is less than 2 and even. Okay, so let's think about how many cases we have here. If the roll is less than 2, then that forces it to be 1. And it can't be even at the same time because 1 is not an even number. So when we look at this event here, roll is less than 2 and even, this is impossible. And the probability of an impossible event is 0. So now we're told that an experiment has possible outcomes A, B, and C. We know that the probability of A is 40%. And we know that B is 3 times as likely as C. Based on that, we want to find the probability distribution. Well, in order to find the probability distribution, we need to figure out the probabilities for events B and C. So let's think about how to start here. Key information is that B is 3 times as likely as C. So probability of B is the bigger number and probability of C is the smaller number. What we could do is we could say, let probability of C be just some unknown number. Let's call it X. If B is 3 times as likely as C, then that tells us probability of B is 3 times X. So at least now we've got some symbols to work with. Now the key insight to solve the problem is that this experiment only has 3 possible outcomes, A, B, and C. So let's think about what happens if we add up the 3 probabilities. Let's add probability of A plus probability of B plus probability of C. These must add up to 1. So that's just another way of saying these must add up to 100%. So let's plug in here and we'll be able to figure out what X is. So we have probability of A is 0.4, probability of B is 3x, and probability of C is X. And if we add all those up, we are getting 1. So let's subtract 0.4 from both sides. We'd have 0.6 on the right, and we can also add up our 3x and our x to get 4x. So 4x is 0.6. Divide both sides by 4, and you've got x equals 0.15. So now we have our probabilities for B and C. So I'm just going to write those out before we build our table. So probability of B we said was 3x, so that's 0.45. And probability of C we said was just x. So probability of C is 0.15. And now we've got all the information we need to write down our probability distribution. So what we want is to list out our different outcomes, and beside those, write out the probability of each of those outcomes. So our outcomes were called A, B, and C. We're told in the question, probability of A is 0.4, and we've just figured out probability of B is 0.45, probability of C, 0.15. And there we have a complete description. We've listed all the outcomes in our sample space, so all the different outcomes that can happen. And when you add up the probabilities of all those different outcomes, you're guaranteed to get 1. So now let's talk about the inclusion-exclusion principle. We actually saw this back in chapter 3 when we were talking about sets, but we wrote it in terms of number of elements in a set. We said number of elements in E union F is equal to number of elements in E plus number of elements in F minus number of elements in the intersection. And actually, we had our sets called A and B, so I might just write it like that so that this looks even more familiar. So we would have said N of A union B equal to N of A plus N of B minus N of A intersect B. So hopefully that looks familiar. Now, we're just going to do another version of this for probabilities. So instead of saying N, we're going to say probability. And instead of calling our sets A and B, we're going to call them E and F, just because that's a bit more common when we're working with probabilities. So probability of E union F equals probability of E plus probability of F minus probability of E intersect F. And we can draw a little picture just to understand why that would be true. So imagine that we had a Venn diagram going representing our different events E and F. E union F is everything inside one or both of the circles. And another way to think about that, if you were trying to get the total shaded probability here, another way to do that would be to just add up the total probability in E and then add up the total probability in F. The problem is that you've overcounted the stuff in the middle here. It's been counted twice, so you just need to subtract off the probability of the intersection, and then you have a correct count for the probability of E union F. So let's say we're given probabilities for E, F, and E union F. And based on that, we want to find the probability of E intersect F. So this is a perfect place to use the inclusion-exclusion principle. We're going to say probability of E union F is equal to probability of E plus probability of F minus probability of the intersection. And we'll just plug in everything that we know. So probability of E union F, 0.65, and on the right side, probability of E is 0.6. Going to add that to probability of F, which is 0.5, and we're going to subtract off this unknown probability that we're going to try to solve for. So the 0.6 plus the 0.5, you can add those together to give us 1.1, and let's subtract 1.1 from both sides. So we're going to have negative 0.45 is equal to negative probability of E intersect F, and then we can divide through by the -1 to get our answer. So 0.45 is equal to the probability of E intersect F. Okay, part B, let's draw a Venn diagram. So we're going to draw a Venn diagram representing the different probabilities of the different regions. So we're going to let E and F be represented by circles, and we're going to try to fill some probabilities into each of these different regions. So we've just figured out from our last step that probability of the intersection is 0.45. So that's going to go into the middle here. E intersect F is the region that's common to the two circles. We were told in the question that the probability of E is 0.6. So you want the entire circle for E to add up to 0.6. Therefore, this number here is going to have to be 0.6 minus the 0.45 that we've already accounted for. So that will have to be 0.15 so that everything in E adds up to 0.6. And in a similar way, we could figure out this probability here. We were told in the question that probability of F is 0.5. So on the right-hand side of the circle for F, we got 0.5 minus the 0.45 that we've already accounted for. So that's 0.05 over in that region there. And then once you've done that, then you can figure out your last probability just using the fact that the sum of all your probabilities has to be 1. So I've just redrawn a fresh version of this diagram so that we can see our last step of reasoning. To get the probability of the outer region, we're going to say, well, sum of all these probabilities has to be 100%, or in other words, it has to be 1. So just go 1 minus and subtract off everything we've already accounted for, subtracting off the 0.15, subtracting off the 0.45, and subtracting off the 0.05. And what you get is 0.35 for this outer region. So that's now a complete Venn diagram that tells us the probabilities of all the different events that could happen. So to be sure that we understand this, let's do a quick part C. So let's find the probability of the complement of E intersected with F. So if you prefer to put this set language into more everyday language, remember complement of E is not E, and the intersection is read as an and. So this is like not E and F. In other words, we're looking at that region that is in F and at the same time is not in E. That would be this region here in our Venn diagram. So just from looking at our diagram, we can read off the probability, 0.05 or 5%. So now for a more real-world application of the inclusion-exclusion principle, we're told that a company has 2 suppliers. Probability that supplier 1 is late, 20%. Probability that supplier 2 is late, 15%. And probability that both suppliers are late, 8%. We want to find the probability that neither is late. So I'll show you 2 ways to do this. You can either reason using algebra, or you can do some visual reasoning using the Venn diagram. So I think I'll do the Venn diagram way first. So let's imagine our Venn diagram, and let's say our sets here represent a supplier being late. So this left circle represents supplier 1 is late, and the right circle represents supplier 2 is late. Okay, let's see what we know. So probability that both suppliers are late, that's 8%, and that goes in the intersection of the 2 circles. Probability that 1 is late is 20%, but that 20% is spread out over this entire circle. So we have to do a little subtraction here and say this probability here is going to be 20%, or 0.2, let's say, minus the 0.08 that we've already accounted for. So that's 0.12. And if we do a similar kind of reasoning over here, probability that supplier 2 is late is 0.15. But that 0.15 already has 0.08 accounted for. So if we do that little subtraction here, that's 0.07 here. Then, once we've got those 3 regions figured out, we can say, well, anytime we're talking about probabilities, the sum of all the probabilities is going to add up to 1. So to get this outer number, we could go 1 minus each of the probabilities that we've already accounted for. So 1 minus 0.12, minus 0.08, minus 0.07, and we get the probability of this outer region, which is 0.73. So now we've got a completed Venn diagram, and from there we can answer any question that comes up. So what are we trying to figure out? We want the probability that neither is late. So we want to be outside the circle of 1 is late, and we want to be outside the circle for 2 is late. So that leads us to the outer region, and the answer is 0.73, or 73% probability that neither is late. So let's call that method 1. That's where we reason using the Venn diagram. Method 2 will do essentially the same thing, but with algebra. So we're not going to draw a picture this time. So suppose we use the inclusion-exclusion principle. Instead of saying probability of E union F, we're going to actually write out what the events E and F are in this problem. So E is the event that supplier 1 is late, and we're talking probability that 1 is late or 2 is late. That's what the inclusion-exclusion principle helps us calculate. So the probability of this or that is probability of the first thing plus probability of the second thing minus probability of both things happening. So minus the probability that both are late. Okay, and so we've got all this information given in the question. Probability that 1 is late, 20%. probability that 2 is late, 15%, and probability that both are late, 8%. Okay, so let's plug in all those numbers there. So 0.2 plus 0.15 minus 0.08 gives us 0.27. So this is the probability that 1 is late or 2 is late. And that's not quite what we want in the problem. Let's go back and see what the problem is asking. We're trying to find the probability that neither is late. Well, neither being late is the complement of 1 is late or 2 is late. So we're just going to say probability that neither is late is 1 minus the probability that 1 is late or 2 is late. So that's 1 minus the probability that we just calculated, which is 0.73. So we definitely end up with the same answer as before, 73% that probability. 73% probability that neither is late. So that's two ways of solving the same problem. I would say the Venn diagram is probably a bit more user-friendly, just helps keep things organized. So last little topic that we're going to look at in this video is the idea of odds. So something that you might hear in the real world is a statement like, say, the odds of winning are 2 to 1. So let's take a statement like this and see if we can turn it into a statement about probabilities. So when we say the odds of winning are 2 to 1, what this means, you are twice as likely to win as to lose. So when you're talking about odds, it's good to think about things in parts. You have 1 part losing and 2 parts winning. So if you wanted to draw a picture of this, you could say if that represents your likelihood of losing, your likelihood of winning is exactly 2 times that. So 2 parts winning, 1 part losing. Now, if we turn that into a probability, so if we're talking about winning, that's 2 out of 3 outcomes. And if we're talking about losing, 1 out of 3 outcomes. So odds are actually referring to the number of outcomes, 2 and 1, whereas when you're taking probabilities, you're taking your number of outcomes divided by the total number of outcomes. So let's see if we can find a way to move from odds to probabilities. So here's our fact that's going to be important. If the odds of an event are A to B, then the probability of the event is A over A plus B. So let's think of it this way. A and B are the number of outcomes. A outcomes where the event happens, let's say, and B outcomes where the event doesn't happen. So your total number of outcomes is A plus B. And when you're calculating probabilities, that's what you're dividing by, is your total number of outcomes. Your number on top just represents number of outcomes in which your event happens. So you're going to go A over A plus B to get the probability. So let's see if we can practice just moving between odds and probabilities. Let's say part A, the odds of getting a promotion are 2 to 7. Let's figure out the probability of getting a promotion. So think of this as 2 ways to get a promotion and 7 ways to not get a promotion. When you calculate probability, you want to think number of ways to get your promotion out of the total number of ways. So on the bottom, we're supposed to be adding the 2 plus the 7 to get 9. So 2 out of 9 is our probability of getting a promotion. You can just follow this formula here. If the odds are A to B, probability of your event is the first number divided by the sum of the 2 numbers. So 2 over 9. So part B, probability of passing a test is 95%, and we want to turn this into the odds of passing. So when you talk about odds, you're talking about a ratio between the thing happening and the thing not happening. It's a ratio of probability to 1 minus that probability. So we would start off with something that looks like 0.95 to 1 minus 0.95 is 0.05. Okay, now this looks a bit weird just because we have decimals in here. So when you're taking a ratio of 2 things, you're always free to multiply both numbers by anything you like. In this case, we could multiply by 100 just to clear the decimals. As long as you multiply both numbers, you're fine. So this is like saying there are 95 situations in which you pass the test, but 5 situations in which you fail the test. And the odds are about talking how many ways can the thing happen versus how many ways can the thing not happen. So 95 to 5, okay, you could leave it like this, but because both of these numbers are divisible by 5, you may want to just divide by 5 to get the smallest possible numbers. So if you did that, 19 to 1. So saying probability of passing the test is 95% is the exact same thing as saying the odds of passing 19 to 1. Let's try one more example like this, moving from probability to odds. So let's say we're told that our probability of graduating is 33 out of 36, and we want to turn this into odds. Well, anytime you're moving from probability to odds, the way to set it up is to go probability to 1 minus probability. So that's giving you a ratio of the thing happening to the thing not happening. So let's plug in our numbers here. Probability is 33 out of 36. And 1 minus the probability, well, if you take 1 minus 33 out of 36, it would be a little bit better here just to put everything over 36. So let's take that 1, multiply it top and bottom by 36. So we're really talking 36 over 36 minus 33 over 36. Let's make that 3 over 36, just to have a simplified probability to work with. Okay, now as we saw in our previous example, you can multiply or divide by any number here that makes this easier to work with. So you could, for example, multiply both numbers by 36. So you'd have 33 to 3. And you could even go a little bit further and say, oh, I'm going to divide this by 3 just to get the simplest numbers possible. So if we divide both numbers by 3, it's 11 to 1. So those are your odds of graduating. So that's our video on assignment of probabilities. Thanks for watching.